Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Symmetry is the language of patterns, revealing the hidden structures of our world, from quantum physics to the architecture of the abstract.
Welcome back, everyone. I'm absolutely thrilled to have you here for this explainer. Today, we're embarking on a super high-energy journey. We're going from the very bedrock of algebraic symmetry, literally all the way to the mind-bending edges of logic and theoretical physics. We're going to explore the profound mathematical structures that govern transformations in our universe. And, maybe the coolest part, we'll uncover how some of these systems actually break the fundamental axioms of mathematics itself. It's going to be a wild ride. So here's our cognitive map for today. We'll systematically uncover 5 dense pillars. 1. Foundations in structure and isomorphism. 2. Undecidability and the word problem. 3. Periodic groups via the Burnside problems. 4. Paradoxes with SO3 and Banach-Tarski. And finally, 5. Set theory and the Whitehead problem. Okay, let's dive into this. Part 1. Foundations, structure and isomorphism. We're going to start off in the comforting, perfectly symmetrical realm of classical group structures. Right, so to really understand group theory, we have to start with Lagrange's theorem. It's basically the foundational counting principle for finite groups. It dictates that the order of any subgroup must perfectly divide the order of its parent group. But, how do we actually prove that? Well, it's this beautiful 3-step mechanical process. First, we define an equivalence relation. So X is related to Y if and only if X inverse Y is in our subgroup H. This perfectly satisfies reflexivity, symmetry, and transitivity. Second, we look at coset cardinality. By defining a mapping function from H to the left coset GH, we can prove both injectivity and surjectivity. That means it's a perfect bijection. Literally, every coset has the exact same number of elements as the subgroup itself. Finally, through partition summation, we see that the entire group G is just a disjoint union of these equal-sized cosets. The inescapable takeaway here is that mathematical substructures have to exactly and cleanly divide their parent structures. Building on those classical foundations, we get the Jordan-Holder theorem. You can kind of think of this as the fundamental theorem of arithmetic, but, upgraded for complex non-abelian group structures. It tells us that any 2 composition series of a given group are entirely equivalent. And tools like the wonderfully named Zassenhaus butterfly lemma, great name, right? They force any 2 composition series to have isomorphic refinements. Essentially, it proves that no matter how you break a finite group down into its simple structural building blocks, you are always going to end up with the exact same fundamental pieces. Moving right along to part 2, undecidability, the word problem. As we shift our focus from the 19th into the 20th century, we discover that this classical algebraic perfection, well, it actually has a hard mathematical limit. And that brings us to the word problem. Imagine you're given a finitely presented group. Is there a universal algorithm, like a Turing machine, that can look at any string of generators, what we call a word, and decide in a finite number of steps if that word is equal to the identity element, 1? Can an algorithm always simplify a group expression to perfectly evaluate its truth? This core question set the stage for one of the most stunning mathematical reveals ever, the Novikov-Bohn theorem. So let's deconstruct the logical mechanics of the Novikov-Bohn proof because it is wild. Step 1, they literally embedded Turing machine states and transition rules directly into group generators as commutation relations. Step 2, they applied Bohn's framework using what are known as HNN extensions. By using stable letters, they forced algebraic reductions, called Britton's lemma pinches, to occur if and only if the simulated Turing machine took a valid step. Step 3. They engineered a highly specific word that equals the identity if and only if the Turing machine halts. And here is the massive so what for us. Because the halting problem is recursively undecidable, evaluating that group equation is also completely undecidable. There is a hard limit here. No computer program can ever perfectly solve all group equations. No way. Part 3. Periodic groups, Burnside problems. Let's transition from algorithmic limits into the fascinating trap of periodic groups. This is where infinitely vast structures hide inside seemingly simple rules. Let me pose William Burnside's foundational 1902 question directly to you. If you have a group generated by a finite number of elements, and every single element within that group has a finite order, meaning, if you multiply it by itself enough times, it eventually loops back to the identity, must the entire group be finite? I mean, it seems intuitive that it should be, right? Well, the answer is a surprising, resounding no. In 1964, Golod and Shafrovich completely shattered this intuition. They cleverly utilized non-commutative associative algebras to build an infinite periodic group. By applying the Golod-Shafrovich inequality, they carefully managed the number of defining relations to ensure the resulting quotient algebra remained infinite dimensional, all while every single element was structurally nilpotent. From this, they constructed an infinite, finitely generated periodic group. Finite rules absolutely do not guarantee a finite universe. So, understandably, mathematicians refined the question into the restricted Burnside problem. Okay, if they aren't all finite, can we at least find a maximum upper bound on the size of the groups that are finite, given a specific number of generators and a strict bounded exponent? And finally, the answer to this restricted version was yes. Efim Zelmanov solved this back in 1989. His brilliance was realizing that he could translate the group's lower central series directly into graded Lie algebras over a finite field. By showing this Lie algebra satisfied the angle condition, he forced nopotency. And this nopotency proved there was indeed a global upper bound. This incredible interdomain translation was so absolutely monumental, it literally won Zelmanov the Fields Medal. And this brilliantly illustrates the complete map of the Burnside branches. We have the general and bounded problems, famously yielding negative answers via non-commutative algebra and transfinite induction on words. And then we have the restricted variant, famously solved in the affirmative using Lie algebra theory. It's a perfect, neat snapshot of a century of mathematical struggle, finally resolved. All right, part 4, paradoxes, SO3 and Banach-Tarski. Hold on to your hats for this one because we are stepping into geometric group theory, where abstract algebra flat out breaks physics, resulting in the theoretical duplication of physical matter. Listen closely to this. A solid ball in three-dimensional space can be decomposed into a finite number of non-measurable pieces and reassembled using rigid motions into two identical solid balls. One ball literally becomes two. This is the mind-bending reality of the Banach-Tarski paradox. But how does group theory actually make this possible? It entirely relies on proving that a free subgroup, called F2, exists inside the rotational group SO3. Let's slowly walk through these mechanics. First, we take two orthogonal rotations, A and B, by an angle of the inverse cosine of 1/3. The irrationality of this specific angle over pi is the actual engine of the paradox. We represent these rotations using matrix arithmetic over integers adjoining the square root of 2. Next, we run an inductive word analysis, clearing denominators by multiplying by powers of 3 to track the coefficients modulo 3. What we find in step 3 is the non-identity conclusion. Basically, no non-empty reduced sequence of these rotations will ever result in the identity matrix. You will never ever rotate back to where you started without explicitly retracing your steps. Therefore, the subgroup is isomorphic to the free group F2. Because this free group allows for paradoxical orbit splitting, when applied via the axiom of choice to the points in a sphere, the mathematical volume essentially duplicates. It's like magic, but it's math. Part 5, Set Theory, Whitehead Problem. We now arrive at the ultimate cliffhanger of our explainer. We are entering a domain where algebraic invariants become so incredibly complex that they completely break the standard axioms of mathematics. Back in 1950, J.H.C. Whitehead posed a problem rooted in homological algebra. If an abelian group A has a vanishing first xth functor, written as x1 a z equals 0, which basically just means that every extension of group A by the integer z algebraically splits perfectly into a direct sum, must group A itself be free abelian? Now, for countable groups, the answer was easily proven to be yes. But for uncountable groups, well, that set up Saharan Sheila's groundbreaking 1974 discovery. Now, what's really interesting about this slide is the incredible answer to Whitehead's question. It is both yes and no. Sheila proved that the problem is completely independent of standard Zermelo-Fraenkel set theory. If we choose to live in Gödel's constructible universe, known as V equals L, the answer is undeniably yes. But if we instead assume an alternate mathematical reality governed by Martin's axiom and the negation of the continuum hypothesis, the answer is definitively no. Sheila's proof mechanics here are just astonishing. He built a filtration of A as a continuous ascending chain of countable subgroups. Under the V equals L axiom, he applied what is called the diamond principle to predict intersections on stationary sets, forcing constructive splitting, which proves A must be free. But under Wharton's axiom, he used a Cohen-Post set satisfying the countable chain condition to patch partial homomorphisms together, artificially creating a non-free structure that still met the Whitehead criteria. The answer to this deep algebraic question is entirely dictated by which invisible set-theoretic universe we choose to believe in. It forces us to question the very bedrock of mathematical truth. To synthesize everything we've just covered, take a look at this comprehensive matrix. We rapidly progressed from classical symmetry, where Lagrange gave us exact divisibility via coset partitions, all the way to algorithmic complexity, proving mathematical undecidability. We navigated the nilpotency of the Burnside problems, duplicated solid volumes with paradoxical orbit splitting, and finally arrived at the Whitehead problem, proving that algebra itself is sometimes entirely independent of our foundational logic axioms. Which leaves us with this final burning thought. If our standard axioms of mathematics literally cannot tell us whether certain fundamental group structures are free or not, what other massive universe-altering structural secrets are hiding just out of sight, waiting for us beyond our current framework of logic? Thank you so much for exploring these pillars of group theory with me. Keep learning, keep pushing the boundaries, and I'll see you in the next explainer.
Like what you shared.
This website makes learning so easy. I found all my resources here.
Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.